Good afternoon, everyone. My name is Wojciech Markowski, and I'm a tunnel engineer working for Arup in London. Today, I have a pleasure to welcome you to the first joint meeting between young members group of the British Tunneling Society and the Tunneling Association of Canada. Before we proceed, I have a couple of housekeeping announcements for you. The meeting will be recorded, and the recording will be available to the BTS YouTube channel via the current link. If you have any questions to the presenter, please feel free to post them in the comment section on the right-hand side. We will read them out after the presentation. Please let me introduce Madison Kennedy from Tunneling Association of Canada, who will say a few words about the organization and will introduce tonight's speaker. Madison, over to you.
Thank you, Wojciech. And thank you everyone for joining us today. The Tunneling Association of Canada promotes and advances tunneling within Canada and has chapters across the country. This webinar is part of our Young Members initiative to keep our young members in touch, informed, and engaged. Today we have Michael Dutton here to talk about the time-dependent deformations of shafts and tunnels in the Greater Toronto Area. Michael is a tunnel engineer with Arup Canada at their Toronto office. He's also the TACym member representative for our Ontario chapter and has been instrumental in organizing these talks. He received a Master's in Structural Engineering from Queen's University in Kingston, Ontario in 2012 before joining the underground infrastructure team at Hatch, formerly Hatchmont McDonald in Mississauga. Project highlights include the Great Lakes Tunnel Project, Eglinton Crosstown LRT, and the Ashutt Bridges Bay Treatment Plant outfall. And without further ado, over to Michael.
Wonderful. Thank you, Madison and Wojciech, for your introductions. And thank you, everyone, for taking a time out of your morning, your afternoon, or even your evening to listen to this presentation today. Before I begin, I'd like to acknowledge several key contributors in this field. Principally, that would be Professor K.Y. Lowe at the University of Western Ontario. Professor Lowe has been the primary researcher for the past several decades since the 1970s, advancing the understanding and knowledge on this front. And you'll see his name pop up constantly in today's presentation. I'd also like to thank both Andrew Cushing and John Hart from Arup, as well as their co-author, Joe Carvello of Golder. They wrote an excellent paper, which a lot of the source material for today's presentation is drawn from. Also, to acknowledge is Jimmy Sosatio and Gary Kramer, former colleagues of mine at Hatch, who have also advanced the understanding of time-dependent deformations, particularly when it pertains to numerical analysis and applying them to design of structures. Today's presentation is sorted into two groups. First off, we'll be talking about the geology and the background of these shales in Southern Ontario and discussing the various mechanisms and characteristics that they feature. The second half of the presentation, I'm going to focus on three case studies, primarily the Billy Bishop Airport Pedestrian Tunnel, the Hound Feeder Main, and if time allows, the Heartlake Tunnel. Finally, I'll summarize with a few takeaways and things for you to remember going forward. So the shales in Southern Ontario. This is a map of the region of Southern Ontario by the Ministry of Department of Mines and Resources, outlining all the different types of formations found in Southern Ontario. They've been grouped into a couple of main areas to help you reference where you are. Toronto is in the middle of this map, shown by the gold star, and that's where I am today. Around Toronto is the Georgian Bay Formation, outlined in red, and right beside it is the Queenston Formation. Both these formations are comprised mainly of shale and are what is of interest to today's presentation. The Georgian Bay Shale, which is referenced more than the Queenston Formation, gets a lot more attention because it's what is found primarily around the GTA and where the majority of these projects and infrastructure projects are located. The Georgian Bay Shale is geologically described as a moderately fresh, weathered to fresh, gray to dark gray, and fine to very fine-grained basal shale. It is the formation. It has widely spaced vertical to subvertical joints, as well as closely spaced subhorizontal bedding planes. These bedding planes or interbeds are described as slightly weathered to fresh, also gray, and grained with siltstone, and limestone. The bedding planes are on average of 15 to 30 centimeters thick. If you look at the image on the right, which is a good cross-section of the Georgian Bay Shale, at the top of the image is one of these very thick limestone interbeds. The four main features that are worth mentioning are particularly the high in-situ horizontal stress that is found in these formations. That's in the order of 4 to 6 MPa for measurements in the field. This stress is quite high in comparison to the vertical stress, which is often quite low due to the shallow nature where these are found close to the surface. The rock is also relatively weak and brittle in nature, with very low unconfined compressive strengths, typically on the order of 10 to 25 MPa. The interbeds, however, are much stronger, on the order of 50 to 250 MPa for the limestone, for example. The material is also highly susceptible to slaking due to repeat wetting and drying cycles during excavation, leading to deterioration upon excavation. Due to the deposition formation and the stress history, the Georgian Bay Shale exhibits crust and anisotropic properties and behavior. And the principal feature and the focus of today's presentation is the subject of the time-dependent deformations, or TDD. So before we go further, we should be discussing the nomenclature and what we actually mean by time-dependent deformations. When we think about rock, we're often thinking of two primary mechanisms. We have squeezing. So when you have a weak rock, immediately upon excavation, the rock might become plastic and displace inwards towards the excavation, primarily due to both gravity and stress gradients and redistribution of those stresses. This effect is fairly immediate soon after excavation. Swelling, on the other hand, is much a longer process. It's often the result of volume change of the rock mass due to water absorption or adsorption effects. And because of this slow absorption of water, it's a quite lengthy process and usually requires a significant amount of time to actually notice a change in displacements. So when we talk about time-dependent deformations, the literature is actually trying to capture both of these effects together, both squeezing and swelling, the simultaneous occurrence of both of these happening. That being said, a lot of the terms over the last several decades have used the term swelling just in their nature, and so I'll be sticking to that standard as I describe this further. So let's discuss about the various mechanisms, characteristics, and why we are concerned about them. So as I was mentioning before, this isn't your typical rock swell phenomenon. Looking at the mineral composition of these shales, doing an X-ray diffraction test, we see that there's actually rather small minimum amounts of swelling clay minerals found in the rock. Also, there's very negligible amounts of swelling minerals such as anhydrite or pyrite. So it's not your typical mechanism that people think of when they think of swelling. Lowe and Lee, in a rather landmark paper in 1993, showed that over a period of several weeks, the salinity of a sample, the blue line, slowly decreased over time, whereas the vertical, they were also measuring the strain of the sample, showed to be increasing over time. So they determined that the driving mechanism was this exchange of cations between the salt-rich pore water of the rock mass and the ambient fresh water. So getting a little technical, what that actually entails is the cations leaving the sample from diffusion and fresh water entering into the sample from osmosis. This process propels both the formation of micro and macro cracks, leading to the sample becoming saturated and leading to an increase in volume. So to emphasize that this process of diffusion and movement of water is a rather time-dependent behavior, owing to the fact of now that we have this time-dependent net result. So to summarize, the behavior isn't due to moisture being absorbed into the material, or sorry, it is from that, it's not from a chemical change of minerals found in the rock. There are several conditions that are required to initiate this swelling. Lowe and Lee in that same paper identified 3. So there needs to be a relief or a change in the stress state of the rock mass. There needs to be an excavation, for example. immediately in the vicinity. There needs to be accessibility to water, and that water needs to be fresh. There needs to be an outward salt concentration gradient between the fluid found in the rock and the ambient fluid on the surface. It doesn't necessarily need to be saturated or have water always present on it. It can also be from humid air in the vicinity as well, creating this concentration gradient. Over time, the swell rate reduces. This is just due to the salinity gradient decreasing over time. As the process goes on, the concentration decreases, and so the swell rate decreases. However, as this process goes on, the swelling-induced rock creates a confining stress or a pressure. It gets exerted from this process, which we need to consider. So there's been a fair amount of research for over the last century. As early as the early 1900s, researchers have appreciated this subject. In Niagara Falls, there's which is a rather large waterfall in Toronto, in southern Ontario. There's a power generating station, and engineers started to measure the displacements of the wheel pits and what was happening over time. So we've seen this plot here that starts in the early 1900s. On the vertical axis is movement, and over half a century or more, there's upwards of 1, 2, or even 3 inches of movement, so quite significant. Then in the 1950s, there was renewed interest in this material because the Sir Adam Beck generating station was going to be constructed, and people started looking once again into this phenomenon. In the 1970s, there was 2 principal projects, both the Heartlake tunnel and the Dutton Creek outfall tunnel. They both experienced severe cracking of their spring line. For instance, the Heartlake tunnel, which we'll talk about later on, just within 3 years of its completion, had severe cracking of its spring line, leading to the need for rehabilitation and further research into what happened. The same, very similar effect was seen on this other project as well. So if we take a step back and just look at what's happening on a simple scale, so if we have our elapsed time since excavation on the x-axis and just the deformation of the exposed face, be it a tunnel or a shaft on the y-axis, immediately upon excavation, there is a short-term elastic movement that's just expected from excavation and stress redistribution. Elastic or plastic, it's some amount of movement. After that, the ground continues to move. And that movement is what we're concerned about. If we install a lining at some point at T0 after the initial time, perhaps it's a segmental lining being put in place by a TBM, or perhaps it's the final lining cast in place for a permanent shaft. Once it gets installed, if we draw a line up, we can see how much additional movement has to be, how much additional movement the ground wants to impart. And that additional movement is going to cause a stress on the lining, depending on how flexible or stiff it is. So to recap, the consequences of TDD is additional stress on the lining, which needs to be considered. There's 3 principal ways to do this. You can either, 1, wait. This is a pretty common approach for many projects in the GTA. By waiting 100 or more days upon the initial excavation, a large percentage of the expected movement is going to dissipate and just expand into the exposed open shaft. And so we won't have to worry about percent-wise such a large displacement. The other approach is to apply a compressible material. If you imagine putting in some foam between the rock face and your final concrete lining, if the rock wants to keep moving, that's fine. It can just push on the foam and minor stresses get transferred to the lining. The third approach is to design for it. If you can have a good grasp of how much displacement is going to occur, we have good input parameters. There's enough knowledge out there in the industry now that we can put some numbers to this and design the lining accordingly. So let's talk about how we quantify TDD. So we're returning back to this wheel pit example. I've now taken that information and plotted the values on a log timescale. A lot of the approaches for TDD is to plot things on semi-log scales. It helps show correlations a lot better. So for different depths along the shaft, several different monitoring points were examined, A, B, C, and D. It's quite interesting to see that the measured displacements were quite different at different spots. Overall, a similar magnitude, but different rates. For example, the orange and the yellow line for the first 100 days had very little displacement, and then soon after, at around day 200 or 300, displacement started picking up. Perhaps at this point, some stress has changed in the ground, or perhaps some more fresh water was exposed to the face and displacement started picking up. On the other hand, the blue line shows a very consistent increase in displacements over time. The main takeaway from this, however, is that when viewing the displacements on a semi-log graph, we see a rather linear relationship. So to recap, if we plot that swelling strain, displacement or strain, same thing, against a semi-log scale, we can see a linear relationship. The research has termed this swelling potential as the slope of this line. So for example, in this graph here, 0.223 is the swelling potential of this sample. A higher percentage or a higher swelling potential just means a higher tendency for the rock to swell upon stress relief. Most lab studies are done over 100 days. Generally, we don't look at the effects over the first 10 days. They're deemed to be too short of a period over the grand scheme of what we're looking at here in terms of years. And so we disregard the first 10 days. That leaves us with between days 10 and 100 as a good place to draw correlations from. Now, ideally, it'd be great to have a lab study that runs for hundreds of days afterwards, but that's not practical. We can't have a geotechnical exploration before a project that requires 3, 4, 10 years of data collection before we can draw conclusions. So we're forced to look at just the first 100 days to figure out what's going on. The only other place to look at what happens before the first 1,000 days, for example, or the first 2.5 years, is to look at example projects that have people have gone back, such as those wheel pits in Niagara, and seen what has actually happened. In this, the other point I want to draw is that we often talk about log cycle of time. Log cycle I refer to as between days 1 and 10, or 10 and 100, or 100 and 1,000. It's groups of period on a log plot, and so that's what's literature tends to focus on log cycles as a way of expressing what's happening. If we take this information and we start plotting them against the applied stress to the sample, we can start seeing some interesting relationships between the applied stress and time. So Lowe and Lee, in their 1990 paper, discovered a rather interesting relationship that when stress is applied to the sample, less swelling is observed. If we apply 5 MPa, the sample reduces how much swelling occurs. However, if we apply a lot of stress above a certain threshold called the critical stress, then the swelling pressure goes away entirely. The sample ceases to move. It's contained. This is determined from a type of test called the null swell test, which we'll get to on the next slide. Lowe and Lee also discovered another interesting phenomenon called the pseudo-Poisson's effect. If we apply stress in one direction, such as the vertical y-axis, and we measure the displacements in the other direction, in the horizontal or the x-axis, we actually see a reduction in stress, or a reduction in displacement in that axis as well. So what's going on is if we squeeze in one direction and we measure in the other, there's actually a reduction, sort of like Poisson's effect in mechanics. I forgot to mention in the last page that what we measure in the x direction is often different than the y direction. The sample, being anisotropic, has different properties in both the horizontal and the vertical direction. So the main types of tests to try and quantify these parameters, there's 3. There's the free swell test, that's what's shown on the left. The sample gets put into, it's wetted and put into a reference point or a gauge, and we measure the displacements over a given time period. The semi-confined test in the middle is quite similar, just in this case, a sample has an applied pressure in one direction, and we measure what displacements occur. The null swell test was what I was referring to before. It's a little different in that the sample is exposed to water and a variable load is applied through a load cell. The deformation is prevented to occurring, and instead we look at the changing load over a given time period. give you a quick snapshot of a couple of different projects in the GTA. There's quite a few numbers on the slide, but just to give you a quick overview of how things compare. Generally speaking, the swell potential is fairly, from various samples can be quite diverse, so the engineer needs to apply some judgment in coming up with the parameters. But the difference between the horizontal and the vertical is quite apparent. It's often on the order of 2 to 3 times bigger in the vertical direction than the horizontal direction due to those bedding planes. The critical stress is also quite different depending on where the sample came from. Different depths lead to different critical stresses in just different regions around the GTA. So it's critical to do the proper investigations and not just rely on past projects that may or may not have the same sort of parameters. So let's talk about some case projects. In the GTA or in Toronto, we have our main airport outside the city, but there's also a local airport on the Toronto Islands called the Billy Bishop Airport. Before the construction of this tunnel, passengers had to take a ferry, as you can see in the image here, just to get their baggage or their vehicles across from the mainland on the right to the island airport on the left. To help with logistics of all that and help relieve the traffic, they decided to build a tunnel underneath the lake and in the rock bed below. This was opened in 2015. The mainline shaft on the right-hand side of that previous image is approximately 33 by 14 meters in plan and 35 meters in depth. There's about 8 meters overburden above, which was supported by secant piles, before then anchored into the rock mass below. And then inclinometers were installed behind to monitor what was happening during excavation, as well as the long-term effects. Just to give you an idea of what the rock support was, it was very simply supported by just mesh and bolt to prevent local failure of any small blocks that might fall out and injure people below. Generally, the rock Georgian Bay has good enough strength to remain stable for the period of a construction window. Those boreholes, as I was mentioning, there was 2 of them. One that was quite close to the face, about half a meter away. Another one 3 meters from the face on the mainland side. Over time, this excavation or this plot shows the displacements, horizontal displacements during the excavation period. We can see in the bottom right-hand corner that after excavation finished, the horizontal displacement kept on increasing. This was the effects of the time-dependent deformations. Plotting some best fit lines to this data, we can generally see a very linear behavior after the excavation process finished, and on the order of 4 millimeters per log cycle of time. So that's 4 millimeters from day 10 to 100 and day 100 to 1000. The tunnel was constructed through a rather interesting sequence. The first step was to install a canopy of drift bores using microtubiums. These bores were 1.8 meters in diameter. There was 7 of them across the crown to provide a good support and trying to cut off the water above. After they were installed, workers went through and created cut 1 of the center passage before cut 2 and on either the west and the north and south side. Once completed, cut 3 and the invert was created. Overall, the initial support was provided by light steel ribs in the drifts, but there was no support provided on cut 1 due to the short window that it was going to be exposed. Cut 2 was supported by bolts and shotcrete. Here's a snapshot of Andrew Cushing, one of the co-authors of the paper, standing beside the microtubium, and an example of the steel plates that were in place before they were backfilled with concrete. Looking at the movements of the, engineers went inside these drift bores before they were backfilled, and using a tape excitometer measured what was happening from their convergence. Once again, fitting best lines, we can see a reasonably consistent increase over time. But I'm sure some of you have already noticed that on the vertical axis, we're talking very small amounts of movement in this case. Compared to before, where we had 4 millimeters per log cycle, now we're down to about less than 1 millimeter per log cycle, so a rather small amount, perhaps due to the short duration, or just they weren't exposed to as much water, or perhaps just their smaller nature led to smaller displacements. Some more construction photos, so we can see those drift bores in the crown already backfilled with concrete, providing a safe working area for people below, and the cut 1 underway. Then we had cut 2 enlarging on either side of the tunnel, and they had a frame hung from the ceiling to help the excavators map out the sequence and the geometry. So plotting, so this time we measured the displacements of the openings. That tape excitometer was used on cut 1 to measure the change of the diameter, and then MPBXs were installed into the east and the west walls. The tape X is what's shown in the gray colors, and there's a fair amount of scatter just owing to the rather small, once again, small displacements that are being observed, and the relative precision of the instrument. The boreholes also very small displacements, but a higher precision on the instrument. Best fit lines are once again added, and we can see similar displacements to what was observed in the drift bores. It's always good to check your numerical models. So before the excavations were complete, or started, I should say, some FLAC models were run to try and do some predictions of what was going to happen. A user-created constitutive model was made to determine what was going to happen with the swelling behavior. So the known parameters from the GI were inputted, as well as the known stress state of the ground. And a rather good agreement was predicted from both the FLAC prediction and the observed predictions over time. So that was quite good to see. It's quite also interesting to see the depth of a swelling zone. When the excavation occurs, we're not expecting the entire rock mass for many meters back to be deforming. It's a rather localized phenomenon just right on the vicinity. Anything further back is limited to deformations just due to that critical swelling stress, because it's keeping the rock mass tight, and no swell can occur. Moving on to our second case study is the Hanlon feeder main and water main contract. So just west of the city of Toronto is the city of Mississauga in the Greater Toronto area. And the region of Peel, which oversees the region's water and wastewater master plan. A couple of years ago, but in early 2010, I believe, we're starting to expand their network, and we're installing a new feeder main and water main, shown in the image on the right. I've marked out the 2 shafts that we're going to be talking about with the gold stars, shaft 5 and shaft 7. These 2 shafts were instrumented with inclinometers behind the face to observe what was going to be happening over the long term. Shaft 5 was a circular shaft, just over 13 meters in diameter. Shaft 7 had a rather unique trapezoidal shape, 6 to 9 meters long and about 4.5 meters wide. Just like the Billy Bishop shafts, these were lightly reinforced with mesh and bolt to prevent local failure. Here's an image of shaft 5 on the left and shaft 7 on the right. Design mitigation is an interesting, we talked about earlier on. The designers for these took a couple of approaches in mind. They first off looked at TDD as a low case. They came up with 200 kPa as an additional load that was going to be applied to the shaft wall, and that the final lining must resist. They also considered mitigating the effects through means and methods. The easiest approach, if the schedule allows for it, is to simply wait and just delay the installation of the final lining. The longer you wait, the more deformation should be occurring in the beginning and less in the long run. There's also installation of drain mats. You can see a blow up in the center and what it looks like installed. This created a void of about 200 millimeters thick, a little bit of a gap between the final concrete and the rock face, just to provide a little bit more of a cushion for the rock to push into. Measuring displacements from the inclinometers. The inclinometers are a little more of a noisy instrument than the precision TACym or the MPBX. We see a rather large scatter over time in both these shafts. Trying to fit best lines to this, we can draw some very loose correlations, but just looking at the displacements in this case, they're quite small. I should also mention that the first inclinometer reading was taken place after the shafts were complete, so any displacements that we're seeing here are just solely, or inferred to be solely from the time-dependent deformations, so a rather minimal amount in this case. The Heartlake tunnel is a rather interesting job because it really kickstarted a lot of the research in this field. Built back in the early 1970s by both drill and blast and TBM methods for different stretches of the tunnel. It was about 2.5 to 3 meters in diameter, depending on the different stretches, and featured a final lining thickness of 300 millimeters. In the drill and blast section, the ratio of the horizontal to the vertical stress was very high, a K ratio of 20 to 40, combination of both very high horizontal stress and very low rock cover, leading to very low vertical stress. Soon after construction was complete, the full length of the drill and blast section, 183 meters, began cracking about 3 years after construction. The TBM section, which was in the slightly deeper region, had a lower K, also observed similar damage just at a later, couple years later on. While I don't have displacement measurements to report to you, the crack widths were significant, talking about 6 millimeters of crack, so that's a rather damaging effect and quite bad for a permanent lining. Also, there was lots of movement horizontally along the crack face of 4 millimeters, so constant movement and a lot of concern. So it's quite interesting that this project back in the 70s featured a large amount of displacements, whereas the two examples that I showed feature much less. It's hard to draw conclusions on why this is. Perhaps it's a difference in the in situ stress ratio. The previous projects were very deep compared to this one, which is much shallower. So perhaps just the nature of the stress ratio has a much bigger impact on what was happening. Or this deformation locally in this area had a higher salt concentration, which just leads to a bigger impacts from this swelling behavior. Just to summarize a couple of key features and key takeaways that I want to leave you with is that the results of TDD will lead to additional convergence of the ground beyond the initial elastic response. And may be present for years long after construction, which must be considered in the design phase by the engineers. These deformations are a function of a couple of main parameters. Firstly, the excavation shape because the excavation shape influences the stress redistribution and what the null stress might be in preventing deformations from occurring. The in situ stress is also a rather important parameter because it sets up how much stress is going to be released and how much movement can occur by the rock mass. The swelling parameters naturally are also quite important and need to be well measured. The predictions are have reached, literature I should say has reached a point, and research has reached a point where it's reasonable to predict what's going to happen using numerical methods such as from FLAC or other closed form solutions. However, to do this, we need to have both a good understanding of the rock mass information from quality lab test data, and also a good measurement of what the rock mass stress is, and this is quite hard to do. So the only way to get around this is we would recommend doing a parametric design, having a good sense of both measurements that were recorded during your project's investigation, but also looking at different sensitivity cases based on previous projects in the local area. And of course, monitoring is also very useful, both for validating your design and furthering the understanding of this rock mass behavior and helping others in projects to come. That being said, monitoring is only as good as the accuracy of the instruments that are being put in. If we are expecting to have small deformations, then we need to have good quality sensors to capture the displacements. So with that, I'd like to thank everyone for taking some time out of their mornings, evenings to listen to my presentation, and I welcome any questions. Thank you.
Thank you very much, Michael, for excellent presentation. We have a few questions on the chat. So I'll start the first one. So there's a question, how does the rock squeeze change with the increase in vertical stress?
How does the rock squeeze change with the
increasing depth cover vertical stress?
I don't have a good correlation that I can simply point towards. So I don't have an immediate answer. Let's see. With I guess a higher rock stress and having an excavation surface exposing this, we're going to have a rather large stress gradient being created. So the on the squeezing side, we actually might have a large amount of both elastic and then plastic deformations in the short term, just trying to balance out the stresses in the ground and trying to have the rock mass remain, or just trying to conform to its failure criterion. However, we're trying to monitor it. So short term, there'd be, I would think, a large amount of displacements. In the long term, I would suspect there's going to be a correlation to the impacts on TDD. I don't have a good answer, however, for you.
Thank you, Michael. There's a second question.
Mm-hmm.
So if the pore water salinity gradient is 0, does deformation, swelling deformation still occur?
The research says no. If there's no gradient, then there shouldn't be any displacements. Is the short answer. That being said, I guess the gradient or the salinity isn't often at 0, just because of the nature of this formation. Geologically, there has been some salt trapped into the shale, so there always is this gradient. Maybe it's going to be less than other regions in the GTA, but there will be some. Yes, a short answer is if there's 0 gradient, then we wouldn't expect there to be any deformations.
Yeah, thank you, Michael. There's no further questions on the chat. So I would like to thank you, Michael, again for an excellent presentation. And on behalf of BTSYM, I would like to thank the Tunneling Association of Canada for helping us organize the meeting. And there's one more question, actually, just popped out.
Sure.
I note you added a black liner before concreting. Do you encourage the squeeze movement to reduce long-term load?
A black line?
Yeah, the black liner. The black liner between the concrete and the rock. I think
we're talking about.
Show this. Yeah, the construction photo. Yeah. Yes, that one.
This drain mat behavior installation. It was. I don't have the specifics from this exact project. I can reach out to the fellow who did if we're looking for more information. However, this is a pretty both inexpensive and a pretty simple approach to create a void. Some other more complicated ways, or not complicated, but other maybe more expensive ways that this has been done in the past is by putting extruded polystyrene boards against the rock face. I believe this is actually what was done on Billy Bishop, though I hadn't talked about it before. I didn't have a picture to show that once the rock face was exposed and before the final lining, basically those giant blue boards that you see in construction were put against the rock mass, the rock face, and then the concrete was poured against that. So another simple way of providing a cushion between the rock and the final concrete. Yeah, there's been some research, very recent research on this front as well. If we don't design for the stress, we can mitigate it by putting in some kind of compressible material. Grouts have also been proposed for tunnels. They can be extruded behind the TBM. Instead of your typical two-part grout that hardens within minutes, we could use a more liquid compressible material that provides a bit of a cushion and doesn't transmit the forces to the final concrete lining, the tunnel lining in this case. Good question.
There's one more question. So over what sort of time does it take for deformation to fully dissipate in the shales? There was an example for Heartlake when the line deformation occurred after about 2 or 3 years.
That's a tricky question to answer. The theory would say never, because it exponentially increases forever on a log scale. But we're talking about diminishing percentages as time goes on. So when we're plotting on that semi-log scale of time, I don't have a percentage for you, but a large percentage is going to happen in the first 100 or the first 1,000 days, and then after that, everything becomes quite small. That's why waiting is one of those good means or good approaches. If you can wait 100 days, you're going to chop off, for example, 100 or 50% of your deformations. I don't have the precise number, but if you look at plots of on a log scale, you can work out the math of how much is going to be lost. So,
we keep getting more questions. Yeah, keep getting more questions actually.
Amazing.
So, were there any issues during construction related to the geology and unexpected groundwater conditions, and how did the team solve them? I think it refers to the construction case study you just referred to.
So I should admit that I haven't personally worked on either of these projects. Both my colleagues have much better understanding, so I can defer some of those answers to them, and if they want to reach out to me, I can help connect. That being said, both I don't know about the Hanlon feeder main, but Billy Bishop did have a fair amount of water issues, just being right below the lake and not having any means to dewater. A lot of the jointing allowed lots of water onto the rock face, so we knew there was ample amounts of fresh water exposure. So if the swelling was going to occur, it was given every chance to occur. But yes, water was a problem on the Billy Bishop project, and yeah, there had to be a lot of. I can't speak to the exact method of how it was mitigated, but there was a lot of effort trying to control it and collect it.
Okay. Thank you, Michael. There's no more further questions, so I'll wait 10 more seconds if any question appears. If no, closing the meeting.
Excellent. Well, thanks everyone for taking the time to listen. If you do have a further question or want some more clarifications, I ask maybe they can reach out to the BTS organization. They can connect you to me, and we can go from there offline.
Thank you very much, Michael. I would like to thank you and the Tunneling Association of Canada. And we keep getting more questions, if you don't mind answering them. We just got 3, literally just in the last 2 seconds.
Sure. No.
Is there an analysis done to estimate the rate amount of deformation due to squeezing occurring at different depths, where there's different stress present?
Yes. So that type of analysis does occur. So if you went back to that FAC analysis and did it for different cross sections at different depths, not that this project had that sort of requirement because the tunnel had a pretty constant elevation, yes, you would see different rates just due to the different redistribution of stresses So for a shaft, for example, yes, that would be an interesting thing to look at. I don't believe it was directly for Billy Bishop. But on other projects I have personally, yes, looked at that. Yes, the parameters might change as well if they're sampled at different depths. So it's hard to try and reach a good sense of what's changing and kind of come up with a good bound of what to use for design. But yes, as an engineer, it's good to look at the different depths and trying to work through what your design pressure is, because it's going to be different for the different spots.
There's a question about shafts. So did you observe any cracks in shafts?
On both of these projects, no, I don't believe there were any cracks observed. And looking through literature, I haven't seen any on shafts. One possible explanation for why that happens is to how, I guess, the stresses work around shafts compared to tunnels. I guess looking at the principal stresses on beside a shaft or beside a tunnel, we see the forces flowing around the tunnel, and there's a rather large difference between the vertical and the horizontal stresses for a tunnel. However, on a shaft, what's flowing around the opening is actually rather the two principal stresses in the horizontal direction are fairly similar. There is some skew in the GTA. One is definitely higher than the other direction, but it's not nearly as big of a differential as the vertical to the horizontal. So effects are more commonly seen on shafts or on tunnels than on shafts.
Okay, thank you, Michael. So I can't see any further questions, so I think we'll now close for now. And I would like to take an opportunity to encourage everyone to subscribe to our YouTube channel, and also invite everyone to our next webinar, which will be organized jointly with Tunneling Association of India, and will happen on 24th of July at noon of British Summer Time. We'll host Dr. Cosimo Yosella from ISA, who will deliver a presentation titled Design Approaches to Avoid Problems During TBM Tunnel Excavation. You can find more details on our website or social media. And thank you very much for joining us, and have a good afternoon, a good day. Goodbye.